Hello everyone, welcome to PW Gulf. So as we all know, JEE Mains 2024 is approaching us in the January. So to boost up our preparation and crack the exam, we have started a previous year question series on this channel. So to help you guys revise the previous year questions and speed up your preparation, okay? So in this we will be doing some previous year questions which have come in the exams in the session 22, 21, 20, okay, so that you can know what type of questions are coming, what is the pattern, how many questions are coming. We will be doing some questions from very good topics which hold a very good weightage in the exam. So for today's class, we have kept the topic as wave optics. So without wasting any time, let us move to question number 1. Sodium light of wavelength 650 nanometer and 655 nanometer is used to study diffraction at single slit of aperture 0.5 mm. We are using two different wavelengths. One is lambda 650 nanometers and the other one is lambda prime 655 nanometers. Okay. Now, two wavelengths are used. First one will be having maxima at different points. Second will have maxima at different point. The distance between the slit and screen is 2 meters. Separation between the position of first maxima of diffraction pattern for obtained in the two cases is, okay, we have to find the separation between first maxima. So we will have y1 prime minus y1, okay. This one will have y1 as the first maxima, this one will have y1 prime as the first maxima. We know that first maxima is obtained at 3 lambda d by 2d. So it will become 3 lambda prime into d by 2d minus 3 lambda d by 2d, okay. So we will get the separation will be 3d by 2d into lambda prime minus lambda. Substituting the values, we will get y1 prime minus y1 as 3 into d value is 2 meters divided by 2 into d is 0.5 mm millimeters into 655 minus 650, this corresponds to 5 nanometers, okay. Now solve it, we will get 6 into 10 raised to the power 3 multiplied by 5 into 10 raised to the power 9. So we will get 30 into 10 raised to the power minus 6. Now see, they have answered us dash into 10 raised to the power 5 meters. Convert it into 10 raised to the power 5, 3 into 10 raised to the power minus 5 meters. So this is the separation. Now you have to answer, this is a numerical type question in which you have to answer the value. So what value you will enter is 3, okay. So this 10 raised to the power minus 5 is already given. This 3 will be our answer, okay. This 3 is the answer. Let us move to next question. In free space, an electromagnetic wave of 3 gigahertz strike over the edge of an object of size lambda by 100, where lambda is the wavelength, okay. Lambda is the wavelength of the wave in free space. The phenomena which happens there will be, now a wave is coming with a free speed of 3 gigahertz frequency, okay, and it is striking over the edge of an object lambda by 100. So what will happen? It will scatter. Phenomena observed will be scattering. Scattering will be the answer. See next question. In Young's double slit experiment performed using a monochromatic light of wavelength lambda, when a glass plate of thickness x lambda is introduced in the path of the one of the interfering beams. We are using wavelength lambda, two source. In one of the source we have a plate, glass plate of thickness x lambda. So we know that there is a shift in the entire pattern. What is they are saying? The intensity at the position where central maxima occurred previously remains unchanged, okay. The intensity where central maxima occurred, it means there must be a maxima present instead of central maxima. So we will have 2 into mu minus, we will have mu minus 1 into t is equal to n lambda, okay. if the path difference introduced due to the glass plate, this should be equal to n lambda, then only a maxima will come over here. Okay, this is the shift. So for maxima, first we will take lambda as 1. So 1.5 minus 1 into t is x lambda is equal to, take n as 1 into lambda, lambda and lambda cancel, we will get x as 1 by 0.5, we will get x as 2. Okay, so this will be the answer. 2 will be our answer. Okay, so see, next question is, in a Young's double slit experiment, an angular width of the fringe is 0.35 degrees. Okay, angular width of the fringe is 0.35 degree on a screen placed 2 meters away for a particular wavelength of 450 nanometers. Okay, angular width of the fringe when whole system is immersed in a medium of refractive index 7 by 5 is 1 by alpha. Now we know that when we immerse the medium in a medium of refractive index mu, then beta prime will be equal to beta by mu. So substitute the value, beta prime will be equal to, beta is 0.35 degree divided by mu is given as 7 by 5. So from here beta prime will be 0.35 degree into 5 by 7. Now when you solve it, what you will get, beta prime will be equal to, this will become 0.05 into 5 degrees. Okay, now remove it because we have to write in the form of alpha. We will get beta is as 1 by 4. So beta prime as 1 by 4. So alpha, this is equal to 1 by alpha. So from here alpha will be equal to 4. This is also a numerical type, so alpha will come out as 4. This will be the answer. Okay, now see next question. Using Young's double slit experiment, a monochromatic light of wavelength 5000 angstrom produces a fringe width of 0.5 mm. If another monochromatic light of wavelength 6000 angstrom is used and separation between the slits is doubled, then the new fringe width will be. We know that beta is proportional to lambda by d. So when we do beta prime by beta, this will be equal to lambda prime by d prime into d by lambda. Okay, so substituted beta prime by beta, this will be equal to 6000 divided by 5000. Angstrom and angstrom will get cancelled out, multiplied by new distance between the slits is doubled. So from here what we will get, beta prime is equal to 3 by 5 into beta. Beta is given as 0.5 mm. So beta prime is equal to 0.3 mm. This will be the answer. 0.3 mm will be our answer. See, very basic question come out of wave optics. Just put the simple formula and you will get the answer. There is nothing much tough in these questions. You can easily go for these questions. So don't miss such topics which have a huge score, okay, which can give you good marks without any negative marks. Okay, so you can attempt these questions easily in the exam. Okay, next question is, in a double slit experiment, when monochromatic light fringes are obtained on a screen placed some distance from the plane of slits. If the screen is moved by 5 into 10 raised to the power 2 meters towards the slit, okay, so screen is changed by this much distance. So d minus d prime is 5 into 10 raised to the power minus 2 meter. This is the distance by which screen is moved towards. Now d prime is less. So d minus d prime is 5 into 10 raised to the power minus 2 meter. The change in fringe width, we know that fringe width is directly proportional to d. So beta, if Distance decreases, beta will decrease. So beta minus beta prime, because change in fringe width is 3 into 10 raised to the power minus 3 centimeter, which is 3 into 10 raised to the power minus 5 meters. Distance between the slits is 1 millimeter. Wavelength of the light used is, we have to find wavelength of the light used. So substitute beta minus beta prime will be equal to lambda by d into d minus d prime. Substitute it, beta is equal to lambda d by d. So we will get beta minus beta prime is this. Substitute the value, 3 into 10 raised to the power minus 5 into d will go to that side, it is 1 millimeter. So divided by d minus d prime, 5 into 10 raised to the power minus 2 is equal to lambda. From here we will get lambda is equal to 300 by 5 into 10 raised to the power minus 8. So lambda will be 60 into 10 raised to the power minus 8 meter. See, we have to express the answer in nanometers. So converted, this will become 600 into 10 raised to the power minus 9 meters. So lambda will be 600 nanometers. Okay, this will be the answer. You will write the result as 600. Okay. See next question. A galaxy is moving away from the earth at a speed of 286 km per second. Galaxy is moving at what speed? 286 km per second, which is equal to 2.86 into 10 raised to, or better write it, 286 into 10 raised to the power 3 meter per second. Okay. Shift in the wavelength of a red line at 630 nanometer is x into 10 raised to the power minus 10. Shift is given as x into 10 raised to the power minus 10. The value of x to the nearest integer is, we know that using Doppler, delta lambda by lambda is equal to v by c. So shift is given as x into 10 raised to the power minus 10. Find delta lambda. This is meters. Okay, I think meters is missing here, in meter will come. Delta lambda will be equal to, what is v? It is 286 into 10 raised to the power 3 divided by 3 into 10 raised to the power 8 meter per second multiplied by lambda, that is 630 nanometers into 10 raised to the power minus 9. So we will get 3 ones are 3. So multiplied, delta lambda is equal to 286 into 21 into, see what it will become, 10 raised to the power, we will have 10 raised to the power 3, 10 raised to the power 4. So this will become 10 raised to the power minus 9 and plus 4. Yes, this will become 286 into 10 raised to the power minus 4. Okay, minus 9 plus 4. From this what we will get, above, sorry, I think my bad, 10 raised to the power 4 and minus 4. Okay, minus 9 minus 4 minus 13 we will have. Sorry, it was my bad, not minus 4, it will be plus 4. Okay, so from here when we solve it, we will get it as 6006 into 10 raised to the power minus 13. We have to express answer as 10 raised to the power minus 10. Delta lambda will be 6 into 10 raised to the power minus 10. So this will be the answer. Meters, here use meters. Okay, so answer you will report is 6, because 10 raised to the power 6 is all, minus 10 is already given. You will report the answer as 6. See next question. Fringe width of 6 millimeter was produced for 2 slits separated by 1 millimeter apart. The screen is placed 10 meter away. The wavelength of light used is x prime nanometers. Value of x prime to the nearest integer is. Okay, so see, Fringe width beta is given as 6 millimeters and beta is equal to lambda d by d. Substituted 6 into 10 raised to the power minus 3 into d. What is d? 1 millimeter. So 10 raised to the power minus 3 divided by capital D, which is 10 meters, is equal to lambda. So from here we will get 6 into 10 raised to the power minus 7 is equal to lambda. So substituted, we have to put it in 10 raised to the power minus 9 because we have nanometers, okay, x prime nanometers. So lambda will be equal to 600 into 10 raised to the power minus 9 meter. So from here we will get lambda is as 600 nanometers, okay, 600 nanometers. So this is the answer. X prime is 600. You will enter the integer as 600, okay. Is this clear? See next question. In Young's double slit arrangement, slits are separated by a gap of 0.5 mm and the screen is placed at a distance of 0.5 meter from them, okay. The distance between the first and third bright fringe. Now see, first bright fringe, second bright fringe and third bright fringe. What is the difference between two successive bright fringe? Distance between two successive bright fringes beta. Distance between two successive bright fringes beta, okay. The distance between the first and third bright fringe distance will be 2 beta, okay. Distance between 2 beta. We have first maxima, second maxima, third maxima, first, second, third. This is also beta, this is also beta. So this will be 2 beta, okay. So distance S is equal to twice of beta, okay. We are given the lambda, substitute it. S will be 2 into lambda d by d. Substitute the value. 2 into lambda is 5890 into 10 raised to the power minus 10 into d is given as 0.5 meter divided by it is 0.5 millimeters. So minus 3, 0.5 gets cancelled. S will be equal to 2 into 5. What we will get? 2 nines are 18 and 17 and 11. 1178 into 10 raised to the power. See, 1178, 10 raised to the power minus 3 plus 1, 4 and minus 6. Okay, so this will be the answer. 1178 into 10 raised to the power minus 6 meter. Option number 2 will be the answer over here. See next question. The speed of electrons in a scanning electron microscope is 1 into 10 raised to the power 7 meter per second. If the protons have the same speed, okay, protons are having the same speed, are used instead of electrons, then the resolving power of scanning microscope will be changed by a factor of. We know that resolving power is inversely proportional to lambda. Resolving power, this is inversely proportional to lambda, okay. If this is inversely proportional to lambda, tell me one thing. We know that lambda is equal to h by p is equal to h by mv. Now mass is different, speed is same. Mass is different, speed is same. So lambda is inversely proportional to m because they have given us same speed. H is a constant, so lambda will be inversely proportional to m. So resolving power is directly proportional to m. Resolving power is directly proportional to m. So if we write resolving power for proton divided by resolving power of electron, this will be equal to mass of proton by mass of electron. So resolving power will be changed by a factor of 1837 because we know that proton is 1837 times heavier than electron. So option number A will be the answer. See next question. In a Young's double slit experiment, 16 fringes are observed in a certain segment of the screen when light of wavelength 700 nanometer is used. Okay, in a certain segment when we use lambda as 700 nanometers. Okay, so we have this much length only. When we use lambda as 700 nanometer, 16 fringes are obtained in this. If the wavelength of light is changed to 400 nanometers, now wavelength of light is changed to 400 nanometers. If wavelength is decreased, fringe width will decrease. So more number of fringes will occupy the same length. Yes, more number of fringes will occupy the same length. Length is equal to number of fringes into beta. We know that beta is directly proportional. Beta is equal to lambda d by d. D and d are same, only lambda is changing. So we have L will be equal to N1 into lambda 1 will be equal to N2 into lambda 2, because L will be equal to, so let us write it like this only, L will be equal to N1 into beta 1 will be equal to N2 into beta 2. Okay, number of fringes occupying, so one fringe is having a width of beta, n number of fringes are coming, so length will be equal to n beta. Substituted 16 into lambda is given as 700 into 10 raised to the power minus 9, or it is given as nanometer only, it will get cancelled, no issues. We can write it as d by d is equal to sum n2 into lambda is 400 nanometer into d by d. Okay, this d by d will get cancelled, that's why we can use the result n1 lambda 1 will be equal to n2 lambda 2. Okay, so from here we will get 16 into 7 by 4 is equal to n2. So from here we will get n2 as 28. Okay, so 28 fringes will come in the same length. Okay, now 28 fringes will occupy the same length, so this will be the answer. See next, interference fringes are observed on a screen by illuminating by two thin slits 1 millimeter apart with the light source 632.8 nanometers. Okay, distance between the screen and the slit is 100 centimeter. Distance between the screen and slit is given as 100 centimeters. So this is D. If a bright fringe is observed at a distance of 1.27 millimeter, they haven't given us that it is first, second, third, which one bright fringe. Only we know that a bright fringe is observed for this much Y. From the central bright fringe, okay, then the path difference between the waves which are reaching this point from the slits is close to. We have to find the path difference. Y is given to us as 1.27 millimeters. Okay, if we want to find Y, okay, if we want to find Y or path difference, this is Y, this is D. Okay, if the waves reaching over here, how much path difference? A bright fringe is formed. Okay, a bright fringe is formed. We know that for a bright fringe, what will be my path difference? Path difference at any point. If you want to see path difference, it will be equal to P is equal to Y d by d. Yes, path difference in the interference came out as Y d by d. Then we keep it equal to n lambda for bright fringe, and we keep it to 2n plus 1 lambda by 2 for a dark fringe. Okay, substituted we will get path difference. Path difference is equal to Y is 1.27 into 10 raised to the power minus 3. D is 1 millimeter, so 10 raised to the power minus 3 divided by D is 100 centimeters, which is 1 meter only. So path difference will come out as 1.27 micrometers. Okay, path difference will come out as 1.27 micrometers. Option number 1 will be the answer. Okay, see next question. Two light waves having the same wavelength lambda in vacuum are in phase initially. Initially both were in phase, two waves having same lambda. Then the first wave travels a path L1 through a medium of refractive index N1, while the second wave travels a path L2 through a medium having refractive index N2. After this, phase difference between the two waves is, now there is a geometrical length, there is a optical length. Okay, if we see optical length is equal to refractive index multiplied by geometrical length. Okay, optical length is mu times geometrical length. So if we want to find optical length of first, okay, L1 of first, it will be L1 N1, and similarly L2 will be L2 N2. So path difference will be path difference is L1 N1 minus L2 N2. So phase difference will be, we have to find phase difference delta phi of phi is equal to, we will have 2 pi by lambda into path difference. So it will be 2 pi by lambda into L1 N1 minus L2 N2. This will be the phase difference between the two waves after traveling these lengths. So option number 3 will be the answer, 2 pi by lambda into L1 N1 minus L2 L2. See next question. In a Young's double slit experiment, light of wavelength 500 nanometer is used to produce an interference pattern. Okay, when the distance between the slits is 0.05 mm, the angular width in fringes formed on this screen is close to. See, angular width is equal to lambda by d. Angular width is equal to lambda by d. So beta theta is equal to, lambda is given as 500 nanometers divided by 0.05 millimeters. Okay, so we will get beta theta will be equal to 5 by 5, this will get cancelled. So we will get 5 into 10 raised to the power 4, 7 and 10 raised to the power minus 2. Okay, we will get beta theta as 10 raised to the power minus 2 degree. Okay, 0.01 degree. Now convert, radian, I'm really sorry, length by length, this will come as radian. Now we will convert it into degree. So beta theta will be 0.01 into 180 degree by pi. So divided by, we will get beta theta is 1.8 divided by 3.14. So when you solve it, this much degree, when you solve it, it will be coming out as 0.57 degrees. Okay, so this will be the answer. Watch it carefully. Lambda by d, both are length, then the angle will come in radians. They have given the options in degrees, so you have to convert it into degrees. Okay, so 0.57 degrees will be the answer. Now let us come to the last question for the day. In a Young's double slit experiment, separation between the slits is 0.15 mm. In experiment, a source of light 589 nanometer is used and interference pattern is observed on a screen kept 1.5 meter away. Separation between the successive bright fringe. Separation between successive bright fringe, this ultimately means fringe width. Okay, this ultimately means fringe width only, because we have to find successive bright fringe. So beta is equal to lambda d by d. Substituted, what is 589 nanometers? 10 raised to the power minus 9 into D is 1.5 meters divided by, we will have 0.15 millimeter. So what we will get? We will get beta as 589 into 10 raised to the power minus 6 into 15 divided by 15, or you will say this multiplied by 10. So simply let us calculate it. Beta will be 10 raised to the power minus 9 plus 3 minus 6 and plus 1. So it will be 589 into 10 raised to the power minus 5 meter. We are given the option in millimeters. So beta will be 5.89 millimeters. Okay, because 5.89 into 10 raised to the power minus 3 meters, which is approximately 5.9 millimeters. So this will be the answer. So these were the some of the questions which were asked in the previous year exams. I hope you answered it correctly and you guys answered so all the questions, every question with me. And see, these type of questions come. Wave optics is a very easy and scoring topic. So first we will be going for the topics which are quite easy and scoring. Okay, target those chapter which can give you easy answers so that you can score well in the exam. Work hard plus do some smart work. Target those chapters which have good weightage and have easy questions. I hope you enjoyed this session and you're looking forward for more such sessions. So take care till then. Goodbye. Do work hard and all the best for your exam. Thank you.